Okay, so incidentally I have about 5 of this color shirts and 5 of the... Anyway, they came at Costco. They were like real good price. So you might see me wearing the same color shirt a lot. I do change my shirt, but it happens to be the same color. Alright, this has been driving me crazy. This book, the 2015 IBC International Building Code. Not really. That's not what we're going to discuss. What we're going to talk about here is shear planes. This book can represent shear planes. See how the pages go back and forth? And I'm going to help you understand concrete and why. So this is not the video. I'm making another video for you guys tonight too. But concrete, the very brittle. Very brittle. The testing that they use on concrete is totally not real world. The samples that they use have nothing to do with the real world. It's just craziness. You don't load it, turn concrete sideways and pressure that way, and it fails in that capacity. After this beautiful crack down the center of this round sauna tube, if you will, they take a dissection of. Now it doesn't fail that way. It fails in the real world by a car simply putting on brakes, as I showed you in the previous video. Putting on brakes, the loading of the concrete there. Concrete sucks. It's very brittle. It's already compressed, so if you do not compress it more, then you're okay. So as long as this can't compress more, which means it won't fracture. So how do we get that? We put it on a surface that won't deflect. So the surface really matters to stop the deflection. Sorry, I thought I heard someone. So the surface really matters, so you don't have deflection. If you take deflection, well then your concrete sucks. Why does it suck? Think about it. I want you to think about this for a second. I'm gonna grab a different sample. Think about this. This is a cross section of a paver. Now, look at it. It's solid. So if it's solid, how can it flex? How can it flex? It's not elastic. It can't flex. Fly. It can't flex because if you try to flex it, this part gets in tension, as we know, and this part gets in compression. That pulls it apart. It separates it. It cannot flex. So now you put this across a deck, someone's floor, and you have this product that will stay flat, but under its own dead load it can't flex, and you get too far out and it wants to just crack on its own dead load. So what do? You put rebar in there, steel, but remember the steel is at first is flexible, as I show you guys. It's very flexible until and it's very flexible. You know what? Let's do this. Let's just take a walk. It's also very flexible. Very flexible, right? Rebar sucks, right? It's got tons of flex in it. All right, tons of flex in rebar. So how the hell can rebar work? How the hell does rebar work if it flexes so damn much? When your car drives on it, you can see it's flexing, right? It's just nothing. This can't work. It can't reinforce concrete, right? It just doesn't make sense. It just doesn't make sense. How can it do that? Well, think about how flexed that was. Now let's go back over here again. The secret's in the book. This book here. So you turn to page 415. Bullshitting, you know I can't help that. So, the secret's in the book. Remember, you're getting all this movement. This is the concrete as one piece. It can't flex, right? It can't flex. If it flexes, you can see that this side becomes compressed, smaller, closer together, and this side gets tension, gets stretched. So I lost my edge here. If I go like this and I kept my hand here, to make this go down, I've actually come closer together in this span here. So it's maybe 10-inch wide book. When I do that, it's now like a 9.5-inch wide book. So you don't get the deflection for free. You have a reaction out here that's pulling, creating tension on those connections, however it's connected. Now watch this. There's this finale. grab yourself a book, do this with the book. Now watch this. Clamp, clamp, clamp your hands on each one of the ends. Now try to flex the book. Now try to flex it. I want you to do that. So grab a book, clamp down tight, and then try to bend the book. As long as you have your clamp force, your book won't bend. Keep an eye on my foxes. I got foxes over there. So there you go. So you're going to clamp, clamp, and then you won't be able to bend that book. I want you to do that. I want you to grab a book and clamp it, one that's flexible. Clamp hard in each one, and try to bend it, and you'll see that you won't be able to bend it. That freezing is what the concrete, when the concrete sets, that rebar and the connections where it connects by each one of the, at the beams, etc., locks this flexible product into place. With limits, that means the loading on it. I couldn't do it with, flex it from here, but if I had, 1,000 pounds, it's going to drop on the floor like nothing else because the supports aren't good enough, and I'm not good enough to hold it 1,000 pounds with like that. So you see the flex. Lock it in here, and now you're going to get nothing. You're going to see that it won't compress. Your rebar inside here, once it locks in, remember the flex thing? Well, now it can't move because it's locked inside the concrete. The concrete normally wants to flex. It's real brittle. It sucks. It's like, it's determined at pretty much about 10%. So 4,000 psi concrete will crack it like 400 psi of tension, just very little bit. I say it's probably even less than that. But the steel, on the other hand, the engagement of the steel, let's just use this piece of wire. The engagement of the steel in the concrete, when it goes to flex, see how this, I remember I'm moving like the book, I'm moving it internal, right? So let me step back a little bit. So I'm going internal, I'm getting closer together. But if I pin this here and pin this here, I can't go closer together. So if I can't go closer together, this becomes taut. And I remember I said I can't go close together because I lock it on each end. It can't come close together, the concrete would have that effect. So if it's locked and you try to put the load on it, it can't shrink up, it can't get closer because, remember, your concrete can't get closer. So if we can stop the flexing in the concrete, if you can stop the flexion in the concrete, you stop it from failing. But if it does flex and it breaks a little bit, you measure that hairline crack, and you don't want it to be much. And you watch that hairline crack. If that hairline crack gets wider and wider, that means your rebar is from, say this is concrete on this side and concrete all around here. No gap. Let's use my finger. Now all of a sudden it gets overloaded by, say, a tractor trailer. A little bit of slippage happens, and then it opens up. And that's okay. And the cars ride on it, and it doesn't open up anymore. All of a sudden another heavy tractor trailer gets on it. It stretches and opens more. Now you're losing, you're breaking the force. I know what it looks like. So you're breaking I mean, I'm a good joker, but I'm going to pass on this joke. So you're breaking the amount of the surface interaction with the rebar that it has on that steel, the rebar. So yeah, that was terrible, wasn't it? I saw that shot. Rebar. So the rebar has those ribs on it. When the concrete sets around it, is this the Portugal one? Nope. This one's doesn't quite, can't make out where this one's made. It grips, and now you can't deflect it. Notice the deformation of it. It's not really deformation because it's designed that way. That concrete and the paste will lock around there, and so now when that does it, it gives you that freeze in time of the concrete. And when your concrete's loaded, it tries to flex, right? But it can't flex because this is embedded inside the concrete, and now it can't flex because it won't deflect because the concrete's holding it in place all around it. The paste is locking this in, so it can't push. It can't with the loads that you applied, the design, the loads you're allowing for 40 pounds per square foot. this will support the concrete, the dead loads, plus the 40 pounds per square foot live loads, the loads that go on and off the structure. They count some dead loads on there too. There's some extra, like a refrigerator might be considered a dead load. But so now, how do you get this to fail? Is that you overload the structure and it starts to flex. And that rebar, and the rebar bends also. You get it breaking down here that I just described. You get it breaking down there, but it's still holding engaged in the concrete. So you just gave it a cycle. You cycled it one time in there. So now you do it a few more times, and you start cycling that steel, and it's starting to make a wear. It's starting to ream out where it was supporting in the structure. It starts to ream it out and break free. And the videos we see, the images we see online, we see that there's not much cover. They got about 3/4 inch or an inch or so concrete above it. So that's not much for it to pull out of it. Not as much as if it was encapsulated, more so. It does matter where you put the steel, depending on how you're loading. There's an overhang, you put it near the top, and you put some at the bottom too. But if you're going from span to span, you know, remember span to span, tension-wise, you say this is a span, that's a span. Exaggerating the weight down the middle here, you can see what happens there. So we don't want it to do that, so we put it at the bottom. So when this tries to do that, this steel becomes active. It's passive, it's just lying there until you load it. It becomes active and it wants to stress, hold on. The cracks are indicators that you've actually now stressed your concrete and your steel are slipping. They're indicators that they're slipping because your concrete deformed so much so that it created a fine crack. That is exactly where the stress is resolving itself based on whatever load created that issue. So whatever load created that issue. But otherwise, it's an internal stress that you can't see when you're loading it. You can't see it, but it's there. Just like this book, when you lock it here and here, I don't want you guys to do that, and then try to push down with your thumbs as you lock it. It's there. That you know it because you're trying to bend this book as I told you to do, and you'll see that. You'll know the internal stresses are there. And it only takes just a little bit more maybe to break that, but it would be broken in your grip. So I want to end the video with that and tell you about, I'm looking at there, sorry about the head chopped off thing, to tell you about how the steel engages, how it matters. That's why we want more steel to cover the spans, 2 directions. And it's another topic about how they go from 2-directional steel. I'm trying to make a short version of it. So imagine 2-directional steel. It still would be better if it was on top of a column or in a beam, not just floating in the middle like plywood. You know, plywood. If you don't put it on top of a board, on top of a floor joist, it will deflect. If you just let it go wild on the outside edge. So we don't want that. And that's the same thing with the concrete, doing the same thing. It will want, on the side edge, it will want to deflect. On the other end, it wants to, you know, it's working, this is its way it works. On the other, I'm trying to, let's go to the thing right here again. So as our car drives across, it transfers the load from one to the other. Remember how I just said how it protects you with the steel not being able to flex. But if you overload it, you know that because you have cracks, and it transfers over. If you're going this direction, you're loading one piece of steel. Well, depending on how it might be plenty, as long as your loads are under what they need, what they specify, 40 pounds per square foot. But say you're driving along and it's okay, and all of a sudden you slam on brakes. Look what happened. You just charge that concrete and excessively over what it does, and now you might get some cracking. You do that for 40 years, cycling it, and you get failures. Cracks matter. Cracks are very important and very telling on what a structure is doing. It really does. All the cracks matter. The finest of cracks matter. All right. If you are going to do a driveway, I recommend pavers. Bye.